Hello all, once again welcome to the LJ Institute of Engineering and Technology. Let's start with our subject mathematics 2. Today we have same chapter series solution of ODE, and last topic of this chapter is recurrence relation for Jn of x. That means recurrence relation for Bessel's function of first kind of order n. Okay, so let's start with the first basic identities, and by using these basic identities we will just give the proof of recurrence relation. Okay, the first basic identity is d by dx of x raised to n jn of x is equal to x raised to n jn minus 1 of x. So to prove this, first we'll write down the Bessel's function of first kind of order n. We know that jn of x is given by this. Now we will multiply this jn of x by x raised to x raised to n on both the side. Okay, so multiply both the side by x raised to n, so x raised to n and x raised to n. This x raised to n goes with this x, so we have this 2 raised to n plus 2m as it is, and this x raised to n plus 2m and plus n, so 2n plus 2m. Now we will just differentiate this on both the side with respect to x. So we have d by dx of this, so we got the left hand side. On the right hand side we will differentiate with respect to x only this term, because all other terms are constant. Okay, so power goes forward and one power minus, so we have this d by dx of this, and this constant, everything is constant. Just we have this power forward or power minus. Now we'll just simplify. So we have x, we can take x raised to n outside, so we have remaining this term as it is, and we can use this formula gamma n plus m plus 1 is equal to gamma n plus 1 n gamma n plus 1. We have this formula also, gamma n plus 1 is equal to n gamma n. That concept we can use here, and we have this 2 common, so 2 goes with this 2, so 2 raised to n plus m minus 1, so this become n plus m, and this x raised to n plus 2m plus 1, because we taken this x raised to n outside from this. Okay, that's why. So by simplifying this, we can cancel out this 2, so we have remaining this term, and x by 2 raised to n plus 2m minus 1. Now we know that jn of x is given by this. So if we put n is equal to n minus 1, so this n minus 1 gives us gamma m plus n plus m. 1 cancel out, and this n plus 2m minus 1. So this is exactly look like j of n minus 1 of x. Hence the proof, simple. And this formula also written as, if we take integration on both sides, so this will cancel out, and integration of this. So integration of x is to n j n minus 1 of x is equal to this plus c. From this you can also find the value of d by dx of x j. If we put n is equal to 1, so j1 of x is equal to x j0 of x, because if we put x is equal to 1, so 1, this is 0. Okay, so we can use also this somewhere whenever we require. Similarly, we have second identity is given by this. We have to prove this, d by dx of x is to n minus n gn of x is equal to minus x is to n minus n jn plus 1 of x. So same way we'll start with the Bessel's function of order n. So we have this, and we'll put x raised to minus n on the both hand side. So we have this minus n. So this minus n multiply with this power, so this become x raised to 2m. Okay, x raised to 2m, and 2 raised to n plus and 2m is as it is, and this is the constant. Now we will simplify, that will differentiate both sides, because we need differentiation. So differentiation of this, and these are the constant, and only differentiation of this x is to 2m. So we have this. Now we can simplify by this, we can take 2 here, so we have 2 raised to this, so 2 raised to minus 1 here. Okay, and by this m cancel out with this one, we have this term, and by replace m by m plus 1, we will just here, because we are differentiating with respect to x, so this become 0 for m, and m is equal to 0, so we start with m is equal to 1. We will put m is equal to m plus 1, so m starting from 0, and by simplifying this, again you can see that this is nothing but our jn plus 1. jn plus 1. If we put in this, we will find this. Okay, so we have jn plus 1. This is our final answer. Okay, and similarly you can write down by taking integration of this. So integration of this is equal to this, by cancel out this, minus goes here. Okay, so these are the two identity that you have to remember, and using this two identity we have this recurrence relation. Okay, number one, we want to prove this. So first, by identities, 1 time d by dx of x is to n, jn of x is equal to x is to n, jn minus 1 of x. Now we'll just differentiate and we'll use product rule. So first as it is, derivative of second, second as it is, derivative of first, and this as it is. Now divide by x is to n. So divide by x is to n. So x is to n cancel out, x is to n cancel out. So x is to minus 1 as it is, x is to n cancel out. X is to minus 1, that is 1 by x. So n by x. So this is our proof. Simple. So simple proof of Bessel's. Okay, so Bessel's function is more easier than, more simple form than Legendre polynomial. Now we have second similar, we will use second identity and we'll differentiate this. First as it is, differentiation of second, second as it is, differentiation of first. Now we'll divide, or we can multiply with x is to n. So this cancel out, this cancel out, this cancel out. So we have this, the answer, simple. Okay, now we have third proof, this. So for that we will use a proof number, that second, for first and second recurrence relation. So we have this first and then second. Now we want to, we want just prove that these two, so these two and jn dash, that means this. So we want to cancel out these two. So by just adding this, cancel out time of this and this. So we have final answer, simple. Similar way, we want to prove this, then again we will use first and second recurrence relation. Now this, we want this and we want to remove this, so we minus plus plus. Okay, so we have this cancel out, this is 2 time, okay, and this is plus plus. So we have this final answer. And from this we can make this subject also if it is asked in this form. So these are the 4 recurrence relation that we have to remember how we can prove. Okay, first and second we can prove from the first and second identity, and third and fourth we can prove from the first and second recurrence relation. Now we have some example that you have to just take a look on this example. We can use here some logic of previous lecture also. Okay, so we know the simple this recurrence relation. Now we will put n is equal to 1 by 2 here. So we have 3 by 2. Okay, if we put n is equal to 1 by 2 to cancel, so this 1 by 2, okay, j 1 by 2 and j minus 1 by 2. Now we have formula for this 2. Already we have proved this 2 value of j 1 half of x and j minus 1 half of x in previous lecture. So we'll use that to formula, and by simplifying this we have the final answer. Okay, similar way we have this example. We want to prove this, so we will use this recurrence relation, and here we will put n is equal to 1. So we have this 1 by x, this is 0. Now by simplifying this, that means this and this, we can take this on the right hand side, we have this answer. Simple, so simple. Now we have this example. So here you can see that we are using only basic identities or recurrence relation, or previous, that j half, j minus half, all this value. Okay, so here we'll start with the left hand side. We can split this x square, so x with this and x with this. Now we have the formula that we already know that. Okay, we can write this d by dx of this. Okay, why we can write this d by dx? Because we have the recurrence relation for this. Okay, and we have the recurrence relation or basic identity this. So d by dx of this, gives you this one. You can see that d by dx of, if you put n is equal to 1, so x j1 of x is equal to x j0 of x. So derivative of this is this. So we know the formula of integration f of x raised to n and its derivative. Then we can write the formula f of x raised to n plus 1 by n plus 1. So this is our f of x raised to n, that means 1. So raised to 1 by 2 by 1 by 2. Okay, so this is the derivative. So this term has a derivative. Ready? Differentiation of this is this. So we can write down this 2 by 2. This is our final answer. Simple. Okay, no need to worry about this. So we have to use here only basic identities. And similar way, we have this generating function for Bessel's function. Okay, same as generating function for Legendre polynomial, we have this generating function for Bessel's function, that just you have to remember the statements. Okay, we are not going to use this generating function in some any recurrence relation or nowhere. Okay, because in Bessel's function recurrence relation, in recurrence relation we already use basic identities. Okay, so these are the DIY that you can solve by using previous lecture of Bessel's and this lecture of Bessel's. Okay, by combining these two lectures we can solve these DIYs. So same here, we are going to finish this entire chapter of series solution. This chapter is divided into three parts. In first part, we find the series solution of any differential equations. In second part, Legendre. In third part is Bessel's. So these are the entire lectures that you have to use pen and pencil, pen, not pen, with this lecture so you can understand better. Okay, so thank you very much for this lecture. We will see you soon with next lecture or some examples. Okay, so thank you very much.